We'll continue in the flow line. So vector field to flow line. So that is the kind of a concept that we will proceed upon. So flow line and vector field. So what is vector field and what is flow line? So I have algebraic equation and then I have a vector field and I have flow line and parametric vector. So that is the concept. Parametric vector came into the picture where we are pushing algebra inside a vector. So algebra on its own cannot provide, algebra has kind of feasibility to provide dependent component based upon the independent component where the variation in the dependent component as per the algebraic equation. So it can be very complex also. For complex kind of variation in the dependent component as per the independent component, we have algebra, but algebra lacks in the direction. If that is the case, then vector is ready-made technology which has direction. So we push algebra inside the vector and it becomes parametric vector. A vector with power of algebra is parametric vector. This is what we are saying. So if I have algebraic equation, from algebraic equation can I get the parametric vector? So that is a matter of research. Now algebraic equation, parametric vector, and I have vector field. Algebraic equation to vector field to parametric vector. So vector field contains property of algebraic equation and parametric vector both. Now from algebraic equation, if I have a vector field, then a vector field to parametric equation, parametric vector, algebraic equation to vector field to parametric equation, parametric vector. So vector field, converting vector field to parametric vector, it is also called, we are calculating the flow line. So reverse of a vector field, either it can be algebraic equation or it can be parametric vector. If it is parametric vector, then we call it kind of uh, flow line. So flow line is analogous to parametric vector. So that is the idea. So from a vector field, how I can calculate the flow line? What is vector field and what is flow line? So we have described it in detail that vector field, if we consider it as velocity vector, vector field is nothing but a vector. Vector field is nothing but a vector whose components are function of xyz. X component is function of xyz. Amazing. Y component is function of xyz. Z component is function of xyz. So rather than saying xyz component, we say if capital F is vector field, then it has components like F1, F2, F3. If F, where F1 is function over xyz, F2 is function over xyz, F3 is function over xyz. So I can say the vector field F, capital F, is function over x, y, z. Okay, if that is the case, then we have F1, F2, F3. Now F1 component, we have to get the flow line. F2 component, we have to get the flow line. F3 component, we have to get the flow line. If vector field is velocity field in the sense that F1, F2, F3 are so full F is a velocity vector where F1, F2, F3 are its components. If that is true, if I have a velocity vector, if I integrate the velocity vector against time, I get the displacement. If I differentiate it further, I get the acceleration. So idea is, can we integrate the velocity vector? That is the gradient, that is the vector field. If vector field represent velocity vector, then if I integrate it, I would get the displacement vector, that is the flow line. Means if person starts from a point and then at each time instance, if I know the velocity of the person, then at each time instance how far he is a distance from that point, I am calculating the time. So if time is 0, then time 30 minutes, 60 minutes, 1.5 hour, what is the velocity of the person at each time? If I integrate it, then at those time, what is the distance from here that I can say? Like from here 5 kilometers, then from here only 10 kilometers, from here only 15 kilometers. So this is the flow line. The distance what we are calculating from the milestone at the beginning is flow line, whereas velocity is the vector field. So flow line, if vector field is velocity field, then flow line will also be a vector. That is integration over the vector field. That is the kind of concept. If that is the kind of concept, then flow line we have to calculate by integrating the vector. So F1, if I integrate, then I get the x component of the flow line, displacement vector. If F2 I integrate, then y component. F3 if I integrate, then z component. Okay. Now suppose that I have equation like the velocity vector is 3i plus 4j, capital F, okay, capital F and XYZ equal to 3i plus 4j. If that is the case, then 3 is F1, 4 is F2. Now 3 if I integrate with dt, then it becomes 3t, and 4 I if integrate with dt, then it becomes 4t. So 3ti plus 4tj, 4tj is the equation of the flow line. Flow line nothing but from velocity vector we are trying to get the displacement vector by the integration. So either we call it flow line or we can call it as parametric vector. Now after that, if I say that this flow line is passing through a point that is -1, -2, then it will become -1 3ti plus -2 4tj. Okay, so if vector field is 3i plus 4j, and then if I calculate the flow line by integrating it, and then I know it passes through -1, -2, then it will become -1 3ti plus -2 4tj, -2 4t in braces, -1 3t in braces, and I and j. So this is the flow line that we have seen. But vector field can be velocity field. Vector field can be gradient field. This is what we saw. So if I have algebraic equation, and from that we have a gradient equation. So in this gradient vector, so vector field can be velocity vector. If I calculate the kind of integration, then I get the displacement vector or flow line. So 3i plus 4j is a vector field. So nicely I calculated the flow line. Suppose I have a algebraic equation of a paraboloid, that is z equal to, or fxy equal to small f, fxy equal to x square plus y square. If that is the case, then vector field, that is the gradient vector, is 2xi plus 2yj. If that is the case, then now gradient vector is nothing but, I think we have demonstrated it nicely in the last session, that if I have kind of a hill, and then if I have we have different cross section of the hill, then in a paper, that is xy plane, if I consider as paper, so we can create the contour as per the cross section vertically we are cutting it. So if slope is less, then if I am calculating, if I am making the circle as per the kind of contour height, then it will be far away circles. But if slope is going up, then the contour will be in near area in the paper only, there will be so many contours, because if uh, if the first contour is at 3 meter, next contour is at 6 meter, next contour is at 9 meter. So we have 3 meter, 6 meter, 9 meter. But and with the x and y, if I have two components, if I take a paper, x axis and y axis in the paper, and then we are drawing contours, you might have seen in many examples. So contour in a way that if I have, this is paper, then this is x axis, this is y axis, then we are drawing circles. Okay, each circle denotes a height. So if I have a mountain and I cut it cross section in vertical, then mountain each height we will place as a circle. So if it is 3 meter, I mean it is very less, 3 meter, 6 meter, 9 meter, then equidistance we will place the circle. Okay, as per the x and y axis variation. Now suppose that at some points height is slope of the hill is like this. Okay, in that case, in very near distance of x and y, there will be too many contours. So, if I see the gradient vector, then gradient vector is a vector, okay, so that is dz by dx and dz by dy. If sz equal to fxy equal to x square plus y square, then dz by dx is 2x and dz by dy equal to 2y. So 2xi plus 2yj is the gradient vector. If that is the case, then that is vector field one. So gradient vector, velocity vector, magnetic field, everything is a vector field. Now, in what sense we are using, that is the concept. But we have algebra and vector both in the vector field. This is what we are saying. Now 2xi, algebra and vector, plus 2yj. Now, if we draw it, then typically what we see 2xi and 2yj, then if it is a kind of circle, then on the x-axis, then it will go like this vector, and y-axis it will go like this. Otherwise, it will go radially. So, if this is the contour, then 2xi and 2yj, that is gradient vector, is perpendicular to the contour. But the place where the contour is height, means in small variation of x and y, the contour starts changing rapidly, then the gradient vector will be like this because it is vertical to the contours. So it will be so the gradient vector is always perpendicular to the contour, and it moves in a direction where the function or z varies maximum. So that is the scenario. But unfortunately, through through Cartesian coordinate, we cannot prove it that what is the direction of gradient vector. Unfortunately, there is no documentation where we can prove the gradient vector is perpendicular to the contour and it moves in a direction that is fastest moving in the function. But anyway, we will see this. Okay, so this is matter of research and we have done it. So we will place that research also, that what is the spatial orientation of the gradient vector. But anyway, now if I have 2xi, 2yj gradient vector, then can I get the flow line? Okay, so if I want to get the flow line of, so I wouldn't say that this is gradient vector 2xi plus 2yj. This is simple a vector field. If equation of a, like in examination someone asks what is sin square theta plus cos square theta, does it mention that it is measuring a road diagram or mountain diagram? Nothing. It is mathematical equation. So suppose there is a mathematical equation vector field at xi plus yj, then what would be the flow line? So for that, the f1 is x and f2 is y. Now if we want to get the x component of the flow line, then I will integrate it with the dt. So we consider as the vector field capital F, if it is, if I am integrating it, means capital F is differentiation of the flow line or parametric vector. If parametric vector is R, then dr by dt equal to vector field F. That's why we are integrating to get the flow line of parametric vector. If dr by dt equal to F, then R equal to F dt integration. If that is the case, then x component is F1 dt integration, F2 dt integration, F3 dt. These are the x, y, z component of the flow line or parametric vector. That is the situation. Now, if we are calculating like this, if it is a kind of xi and yj integration of x dt to get the x component, integration of y dt to get the y component is not possible. Means x is different thing and dt is different. If the algebraic equation was z equal to x square plus y square, if it is 1 plus y square instead of x square plus y square, sorry, if it is x plus y square, not x square plus y square, x plus y square, then vector field will become, a gradient vector will become 1 plus 2yj. In that case, f1 is 1. In that case, if I integrate, it will become t plus x0. x0 where the point through which it would pass. If that is the case, or rather I would kind of modify again, the algebraic equation is x square plus y square. Instead of that, it is x plus x square. X plus x square. So vector field is 1 plus 2xj. If that is the case, x plus x square. Okay. So, or I am trying to kind of x plus x square in a sense, or I can say it as that if the kind of the vector field what I am expecting is 1 plus x, 1 plus x. Okay. So it is something like I can say that okay, so the kind of the vector field equation, I mean, you can imagine it. What my idea is that vector field, what would be generated from algebraic equation that was fxy equal to x square plus y square, for which we are getting 2xi plus 2yj. Now the vector field what we are getting now is I plus xj. I plus xj. Now you can think what would be the algebraic equation after doing the partial derivative. If that is the case, then I means dt integration, that is the tx0. Now if I try to get the x component of the flow line, then I have to integrate f1, that is dt, that is t plus x0. If I try to calculate the y component of the flow line, that is x dt. So x we have got as t plus x0, that I would replace there, and it would become t square by 2 x0t plus y0, where x0 y0 is the point through which the flow line is passing. So x component is t plus x0. Earlier it was 3t minus 1 plus 3t, and y component is t square by 2 plus x0t plus y0. So in earlier case it was passing through minus 1 minus 2. In that case it will become t square by 2 minus t minus 2. Okay, so that is kind of flow line. Now we will proceed. Now consider that the algebraic equation is x square plus y square. Now the vector field is 2xi plus 2yj. Now f1 is 2x and f2 is 2y. If I try to get the flow line, I have to integrate it, and then it is not possible. 2xi dt and 2yt dt is not possible integration, because both are different variables, dt, and then the kind of the function we are trying to integrate, that is x, there that is y. So one has to be constant so that we get the integration, and that we can replace at other places. So here the Euler method comes into the picture. If I have a vector field where f1, f2, f3, vector field capital F equal to, it has component f1, f2, f3, and each are in function of x, y, then calculating the flow line displacement vector or parametric vector where I have to integrate with the dt is not possible. In that case, we will try to get some value through Euler method. So Euler method states that if I have a parametric vector RT is the parametric vector where independent component is T and dependent component is RT. So at T1, if it is R1 and T2 it is R2, then R2 minus R1, R2 minus R1 is nothing but delta R, where T2 minus T1 is nothing but delta T. If delta R by delta T, delta R by delta T means dr by dt. That is nothing but vector field. Dr by dt equal to the vector field. Okay. Anyway, so R2 minus R1 equal to delta R, or R2 equal to del R1 plus delta r. Delta r is the distance between R2 and R1, where R2 is at T2 and R1 is at T1. So now we have equation as R2T equal to R1T plus delta. R2T minus R2T minus R1T equal to delta R. So R2T equal to R1T plus delta R. Now delta R is the vertical distance between R2 and R1. If I want vertical distance, if I have horizontal distance, that is delta T, if I know how it is varying, that is the slope. If I know the rate of change and I know the independent component, if I multiply the independent component with the rate of change, I get the vertical. Okay, that is the general equation. So if I have rate of change, so this is a line. If this is a line and line has this much width and the line as a slope, I know the equation. What is the rate of change? If per unit of the horizontal direction, per unit in the horizontal direction, if vertical is changing 2, if vertical is y and horizontal is x and dy by dx is 2, means per unit change in x direction brings 2 unit change in y direction. If x is if x is 5, then 5 into dy by dx is y, that is 10. Okay, so if I know rate of change, dy by dx means rate of change. If I know the rate of change and if I know the horizontal gap, then if I multiply, I get the vertical. So if I know delta t, if I know delta t, and if I know the rate of change, if I multiply both, then that is delta r. Delta r is the vertical and delta t is the horizontal. I had two time instance, T2, T1, that is delta t. At T2 it is R2 and T1 it is R1. R2 minus R1 is equal to delta R. So delta R is nothing but T2 minus T1, that is delta T into the rate of change that we have seen, that is dr by dt. So if I know dr by dt into dt or delta t brings the dr, means mathematically also, or delta r by delta t, if I know, if I multiply by delta t, then that it becomes delta r. So delta r by delta t dr by dt is the vector field. So now I have R2 equal to R1 plus delta R will be replaced by delta T F, that is the vector. So R2 equal to R1 plus delta T F, F at R1T. This is Euler approximation. R2 equal to R1 plus delta T F at R1. Now, can you see R2 I can calculate if I know R1, if I know delta T, and if I know the vector field at R1. So if I say that my vector field is 2xi plus 2yj and the flow line is passing through minus 1, minus 2. Can you calculate the flow line points at least? So if I consider R1, that is the beginning one, is minus 1 minus 2, then R2 if I want to calculate, then R1 is minus 1i minus 2j plus what is the delta t over we are calculating. I can set any delta t as per our mathematics. What is the, how far we are chopping the t? If I am chopping t at 0.01, then it is 0.01 into f at t rt1. So that is x square I plus y square 2xi plus 2yj. X is minus 1 and y is minus 2. So minus I minus 2j into delta t, that is 0.01, that we have to add with the whatever we got. So 2, so it will become minus ij minus 2j if it is passing through a point minus 1 minus 2, then R1, R1 is minus I minus 2j minus I minus 2j plus 0.01 multiplied by 0.01 multiplied in braces 2xi plus 2yj, that is 2 into minus 1i plus minus 2 into 2 into j. Whatever comes all along, that is the ith component and jth component. They are the x and y component of the flow line. That is the second point. First point is minus 1, minus 2, we started with. Second point is this one. If I know second point, then again we'll come to equation, that is R2 equal to R1 plus delta T F at R2. So, I mean, now equation is R2 equal to R1 delta T vector field at R1. Now, I know R1, I know R2. So, R3 equal to R2 plus delta T F at R2. So, this is the way we can keep calculating. So, at any n plus 1, Rn plus 1 equal to Rn plus delta T F at Rn. So if I know Rn, and then we can calculate Rn plus 1. So this is the Euler method, where at each point, if we say that our flow line, if our vector field is in function of x and y, where we cannot integrate with dt to get the flow line, then we can do the approximation in a way that if I know the flow line is passing through a particular point, that point is the beginning point of the flow line vector. If that is the case, then R1 equal to R0 plus delta T F at R0. R2 equal to R1 plus delta T F capital F at R1. R3 equal to R2 plus delta T F at R2. R4 equal to R3 plus delta T F equal to R3. So this way we start getting the new point along the flow line vector that I can place in a table, and we received the value. If you are very powerful in algebra, then looking at the value at each point, you can deduce the algebraic equation. This is what we are looking for. That if I have x as these many points and y component as these many points at this time interval, then we could not deduce the algebraic equation. This is what we saw. If someone can deduce where the independent component is t, then he is most welcome. So that is the scenario that kind of we presented as Euler method. So in a summary that we will see in the next session, probably we could not end, that where from we started in the parametric vector and finally we ended up in the Euler method to calculate the flow line from the vector field. So if vector field is constant, scalar field, vector field we generate set of vector. If it is a scalar field, then quickly I can calculate the vector flow line integrating with the t, where we understand that flow line is like a parametric vector. If parametric vector is r, then dr by dt is vector. So r is the integration of vector. Vector field has component f1, f2, f3, and each f1, f2, f3 is function over xyz or xt, yt, zt. Whereas the parametric vector or the flow line vector is also a function in xt, yt, zt, xti plus ytj plus ztk. Whereas the vector field f equal to f1, f2, f3, where f1 is function over xt, yt, zt all, f2 is function over xt, yt, zt all, f3 is function over xt, yt, zt all, or I can say f1 is function over xt, yt, zt, okay, I, plus function over another function over xt, yt, zt j plus another function over xt, yt, zt k. So these are the component of vector field. Each component, if I integrate, because each component is differentiation of each component of vector field, like xt, if I differentiate, then xt, if I differentiate, it becomes f1. Yt in the flow line, if I differentiate, flow line and parametric vector are analogous. So if I have xt, if I differentiate xt dxt by dt, then it becomes f2, second component of the vector field. So if I integrate with the t, then it will become xt yt zt. But if vector field is in function of x y z, okay, if it is if f1 f2 f3 are constant scalar, then immediately I can integrate with dt and we get xyz component. If at least one of them is scalar, then I can integrate, and if I get x component and other places x component is there, I can replace the integral value there. Then we can try. If nothing works, then we go for Euler method. In Euler method, we take R or flow line or parametric vector as dependent component over T. In that case, if I have two time instance T2 and T1, for that the parametric vector is R1 and R2. So R2 minus R1 is delta R over the independent component delta T. If that is the case, then R2 equal to R1, R2 minus R1 equal to delta R. So R2 equal to R1 plus delta R. Delta R is the vertical component for which horizontal component is delta T. If I know dr by dt, then if I multiply dr by dt with the delta t, I get delta r. So I can replace delta r with delta t into dr by dt. So R2 equal to R1 plus delta t into dr by dt. So R2 equal to R1 plus delta t dr by dt is nothing but vector field f at R1. Okay, if that is the case, then R2 is completely dependent upon R1 delta t and function vector field at R1. So if I know one point in the flow line through which flow line is passing, that becomes the R1 value. So now I know R1, I know delta t, a function over R1, vector field over R1 means the vector field is in x and y. So that point we will set in the vector field equation, and that vector field we get back as a vector in a scalar. Altogether, if I compute, then I get R2. So R2 I get from the R1. So Rn plus 1 I can get from Rn, previous one. So one by one we keep getting the point through the Euler method. I can fill a table that as these t equal to this, then I get this much x component and this much y component. Rather than getting as a function, we get the value. If someone is very powerful, then no one stops him to get the kind of calculate the algebraic function from the Euler table. So that is the scenario. Okay, so I believe this is fine enough that we will summarize from the beginning to the end of the parametric vector, and that's how we will end. So that we will see.